The ADMS testbed at NREL provides a realistic laboratory environment for utilities, vendors, and researchers to evaluate the performance of advanced distribution management systems and other utility management systems on specific distribution systems. The main elements of the testbed are the real-time simulation, hardware integrated through hardware-in-the-loop techniques, industry standard interfaces, scenario generation, and analysis and visualization. An ADMS or other utility management system is integrated with the testbed through the industry standard interfaces. In this virtual tour, using photographs taken a couple of months before the pandemic, hence the absence of masks, we will start with the Schneider Electric ADMS. The ADMS is installed on a virtual machine within NREL's high-performance computing environment, so all that is visible in our laboratory setup is the user interface. The ADMS is interfaced with the hardware and simulated components of the testbed using the DNP3 protocol. A key element of the simulation is the digital real-time simulator, and for the model quality use case, we use an OpalRT platform. We use Opal's DNP3 libraries to interface with the ADMS. We use Opal's ePhaserSim dynamic phaser simulation tool for this use case to simulate part of the Excel feeder under study. And the rest of the feeder is simulated using EPRI's OpenDSS quasi-static time series simulation tool running on a laptop. The laptop also hosts translator software developed by EPRI that provides a DNP3 interface for OpenDSS so that components simulated in OpenDSS can communicate with the ADMS. The laptop also runs the testbed coordinator software based on Helix that orchestrates the experiments and manages data collection for both real-time visualization, shown on the large screen in the back, and post-processing of results. We also use the digital real-time simulator to interface hardware to the simulation. For the model quality use case, we interface two capacitor bank controllers, a load tap changer controller, and a three-phase 12 kVA PV inverter that is mounted on the back side of the rack. This completes our virtual tour of the testbed. The model quality use case experiments are carried out over 22 hours to capture the voltage management and energy savings over an extended time period. And since the experiments run real-time, we will demonstrate just a single VVO optimization cycle in this video.
To demonstrate the control of the ADMS on the devices, we're going to close two of the capacitor bank controllers. First, we send the close command to the device simulator capacitor bank controller, followed with the hardware capacitor bank controller. Once the simulation is running and all the connected devices are in the correct state in communicating with the ADMS, the system is ready to activate the VVO application. We perform a series of verification steps. First, we confirm the measured density and the model quality are the correct test scenario. We open the control window on a couple of the meters to verify that the correct measured density will be used by the application. Then, we confirm the correct model version is active. Second, we review the VVO profile to confirm the correct objective, constraints, and resources. A final check is done on the power application settings to verify that the VVO will be triggered immediately if any of the defined constraints in the profile are violated. Load flow and state estimation for the feeder is performed for the system to evaluate its current status. The LTC set point is verified that it corresponds to the current ADMS set point before initiating VVO. We are ready to activate the VVO application. We open the ADMS VVO closed loop management tool and set the VVO operation status to active. The VVO then immediately executes its control strategy and issues a set point or change status to its available resources. In this instance, the LTC. From the VVO execution report, you can observe that the new LTC set point value is 118.3 volts. That will give a 4.61% energy savings as per the power consumption objective. The simulation recognizes that the voltage is out of band and starts issuing a lower tap command. The system is configured to execute the VVO algorithm every 15 minutes continuously if there are no constraint violation until it is turned off. To assist with the evaluation of the ADMS, an integrated data collection tool was implemented for data management and 2D visualization to better track the performance of the test and evaluation of the results. Data from the simulation different platforms get streamed to the ESET relay converter. As you can see in the visualization from our test, that we can track the capacitor status in the middle bottom plot. Also, the top right corner plot tracks the LTC set point. The right second plot is the tap position, and the third plot is of the end of line voltage.